In this video, we want to prove some identities about real parts, imaginary parts, and the conjugate of a complex number. First, we want to prove that real of z is equal to z plus conjugate of z divided by 2. And from this, we want to conclude that z is pure imaginary number if and only if the conjugate of z is equal to negative z. Before we start the proof, let me remind you what is real part, what is imaginary part, what is conjugate of a complex numbers. Suppose z is a plus bi. We know that every complex number can be represented in the form of a plus bi. For example, z equals 3 plus 2i is a complex number. Every complex number has two components, two parts. Real part. In this general form, real of z is a and imaginary part of z is b. Attention, imaginary part of a complex number is the coefficient of I. So, imaginary part of z is only b. What is the conjugate of a complex number? If z is a plus bi, the conjugate of z, which we can show with z bar, or sometimes in some textbook they show with z star, is a minus bi. So what is the conjugate of 3 plus 2i? The conjugate of 3 plus 2i is 3 minus 2i. Now that we are familiar with real parts, imaginary parts, and the conjugate of a complex number, let's start our proof. We want to prove that real of z is always equal to z plus conjugate of z divided by 2. To prove this, we suppose our complex number z to be equal to x plus iy. We know that any complex number can be shown in this form. So we suppose z to be x plus iy. Now, from here, let's see what is real of z. We know that real of z is x. Now let's calculate the other side of this identity. What is z plus conjugate of z divided by 2? Z is x plus iy. The conjugate of z is x minus iy. And divide this by 2. So this is z and this is z conjugate. As we can see here, when we add z to its conjugate, iy and negative iy cancel each other. What remains in numerator? 2x. X plus x is 2x. 2x divided by 2 is x. As you can see, real of z is x. This is the definition of real of z. And also, z plus conjugate of z divided by 2 is also equal to x. So this shows that always real of z is basically z plus conjugate of z divided by 2. And this completes the proof. So the two sides are equal to each other and both of them are x. Now from this identity, we want to conclude that if z is a pure imaginary number, this happens if only if the conjugate of z is equal to negative of z. So, attention, here we want to prove two things. If z is pure imaginary, then the conjugate of z is negative of z. And also we want to prove the opposite of this, which is this. If the conjugate of z is equal to negative z, from this we have to prove that then z is a pure imaginary number. Before we start our proof, let's see what is the meaning of this statement that here we want to prove it. What is a pure imaginary number? When we have an imaginary number, let's say z, it has two parts, the real part and imaginary part. The real part is 3 and the imaginary part is 4. But a pure imaginary number is a complex number that its real part is 0. So for example, z equals 5i, z equals 4i, z equals -2i. These are examples of pure imaginary number. We want to prove that if z is pure imaginary number, then the conjugate of z is equal to -z. And also we want to prove the opposite. Attention, this is if and only if statement. When you see in mathematics, if and only if statements, you have to prove two things. You have two sides to prove. So basically here we want to prove this. If z is imaginary number, is pure imaginary, then the conjugate of z is equal to -z. Also we want to prove the opposite of this. If the conjugate of z is equal to negative of z, then z is pure imaginary number. First, we want to prove this side of the statement. We want to prove that if z is pure imaginary, then the conjugate of z is equal to -z. If z is pure imaginary, it means that the real part of z is 0. It doesn't have any real part. So from this step, z is pure imaginary number, immediately we say, from this we conclude the real of z is 0. If real of z is 0, based on this identity that we have here, real of z is 0, so based on the identity that already we have proved it here, 0, attention, real part of the number z, because it's pure imaginary, real part of z is 0. So based on this identity, the left side of the identity is 0. So we have 0 equals to z plus the conjugate of z divided by 2 equals 0. And from this, if we multiply both sides by 2, we can get rid of the 2 in the denominator. So from this we have z plus conjugate of z equals 0. And simply, if we move z to the other side, z conjugate is equal to -z. So we prove that if z is pure imaginary, then the conjugate of z is -z. And the process of the proof was this. Z is pure imaginary, immediately we conclude the real part of z is 0. Because real part of z is 0, we use this identity here. We say the left side is 0, so it means that the right side should be equal to 0. And from this we concluded this result. Now we want to prove the opposite of this relation. We want to prove that if z conjugate is equal to -z, then z is pure imaginary number. So we want to prove that if z conjugate is equal to -z, then z is pure imaginary. But how we prove this? With the aim of this identity. Attention, we want to prove this based on the identity that we have proved it here. Because z conjugate is equal to -z, because, please pay attention to here, we have this here, because z conjugate is negative of z, so this means that this expression in the right side is 0. Because conjugate of z is equal to negative z. Immediately from this, we conclude that z conjugate plus z is 0. Simply add z to the both sides. This side would be 0. We have z conjugate plus z equal to 0. Now, we use our identity that we have proved here. From this identity that real of z is always z plus z conjugate divided by 2, the numerator of the right side is 0. So this means that all of this is 0. Based on this identity, we conclude that real of z should also be equal to 0, because we know that always this is equal to this. If the right side is 0, immediately the left side is 0. These are equal to each other. Here we know that the right side is 0, so the left side should also be 0. What is the meaning of real of z is 0? When real part of a complex number is 0, this automatically means that that complex number is pure imaginary. This is the definition of basically pure imaginary number. Pure imaginary number is a number that its real part is 0. So from this, immediately we conclude z is pure imaginary number. So we prove that both sides of this relation here. Now we want to prove that imaginary part of a complex number like z is always equal to z minus conjugate of z divided by 2i. And then from that we want to conclude that if z is a real number, then the conjugate of z is z, and if z conjugate is equal to z, then z is a real number. This is if and only if again a statement. So first we want to prove this identity here. Our first job is to prove this. The process of the proof is similar to the previous part. You can pause the video here. Try to prove this similar to the proof of the previous part. It's a good exercise for you. I highly recommend you to pause the video here. Let us start the proof. So we suppose z as x plus iy. If z is x plus iy, immediately we know that what is the real of z? What is imaginary part of z? Here we want to prove the imaginary part equals that. What is imaginary part of z? Imaginary part of this complex number is y. Now let's see what is the other side of this equation. Z minus z conjugate divided by 2i. Z is x plus iy minus the conjugate of z is x minus iy divided by 2i. If we subtract numerator terms, x minus x cancels. Then we have iy plus iy, which is 2iy divided by 2i. 2i with 2i cancelled, and then we have y. Look at this. For any complex number like z, imaginary part is y. Z minus z conjugate divided by 2i is also y. So this shows that these two are equal to each other. And this completes the proof of their identity. Now we want to use this identity and conclude that for any complex number like z, that complex number z is a real number if and only if the conjugate of z is equal to z. When a complex number like z is a real number, it means what? It means that its imaginary part basically is 0, because a complex number in general is in this form. When it becomes a real number, it means that the imaginary part is 0 and it has only a real part. So if z is real, So this is the statement that we want to prove. If z is real, then z conjugate is equal to z. And also we want to prove the opposite of this, which is this. If z conjugate is z, then z is real. First, we prove this side of the identity. If z is real, then z conjugate is equal to z. So let's start. Z is real. When z is real, it means what? It means that imaginary part of z is 0. This is definition of a real number. Real number is a number that has no imaginary part. So imaginary part of z is 0. Now look at this identity here. Imaginary part of z is 0. So this is 0. So this fraction here, this expression is also 0 because this is equal to that. So based on the identity that now we know and we have proved it, we can use that identity. Based on that identity, immediately we conclude z minus z conjugate divided by 2i is also equal to 0. If we multiply both sides by 2i, to get rid of the 2i in the denominator, we can conclude z minus z conjugate is 0. And what is the meaning of this? Z is equal to z conjugate, or z conjugate equals to z, which is the other side of this statement. So we suppose z is real, and we prove that the conjugate of z is the same as z. Before we prove the other side of this statement, let me show you some examples of the meaning of this. When z is real, it means what? It means that z is something like 4 or 5 or negative 2. It's just a real number, just a normal number that we use. If z is real, what is the conjugate of this number? Conjugate of this would be again 4. And of course, z conjugate is the same as z. Because conjugate of a complex number is changing the sign of the coefficient of I. When it has no I, so it doesn't change. The conjugate would be the same number. But attention, if z is not a real number like 2 plus 3i, the conjugate would be completely different number. But when z is real, its conjugate is itself. And it's completely clear. So basically, this statement is completely a clear and obvious statement. But anything in math should be proved because everything is based on math in science and other things. So this should be perfect. So that's the reason we prove even something that seems obvious. Now let's prove the other side. We want to prove that if z conjugate is z, so we want to prove 2. From this to that, if z conjugate is z, then z is real. So we suppose z conjugate is z. Immediately remember this relation. Z minus z conjugate divided by 2i is imaginary part of z. Because z conjugate is z, this means that z minus z conjugate is 0. And because this is 0, remember the identity we had. Imaginary part of z is always equal to z minus conjugate of z over 2i. When this is 0, this means that numerator of this is 0. And when numerator is 0, all of this is 0. So, based on the identity that already we have proved, immediately we conclude imaginary part of z is 0, is equal to 0. And when imaginary part of a complex number like z is 0, what it means? Imaginary part of a complex number is 0. What is the meaning of this? This means that that number z is a real number because its imaginary part is 0. And this proves the other side of the statement. Let's continue to the next part. We want to show that real of iz is equal to negative imaginary part of z. Similar to the previous parts, we suppose z a complex number, and when we talk about complex number, immediately we know that z can be represented in the form of x plus iy. So, to prove this, we suppose z as x plus iy. Now we are going to calculate left side and the right side of this, and we will show that they are equal. What is the real of iz? Real of iz is real of I times by z. Z is x plus iy. Multiply I in the bracket. Then you have real of I times x is xi or ix, it doesn't matter which form you write, ix, plus I times I is I to the 2. I to the 2 is negative 1. So I times iy is basically negative y. Now, what is real of ix minus y? Real part of this complex number is negative y. X is the imaginary part and real part is negative y. So, the left side is negative y. Let's see what is the right side. It should be the same, because this is an identity we want to prove. Negative imaginary part of z. So we start with negative imaginary part of the complex number z. Negative of imaginary part of x plus iy. Imaginary part of x plus iy is y. But we have a negative outside, so this equals to negative y. By comparing equation 1 with equation 2, by comparing these two, immediately we can conclude that real of iz is always equal to negative imaginary part of z. Finally, we want to prove imaginary part of iz is equal to real of z. As a good exercise, you can pause the video here and try to prove this by yourself. How we prove this again? We suppose z to be equal to x plus iy. Then, from this, real of z is x. It is clear. Real of z is real of x plus iy. It's better to write it this way. It's more clear then. Real of x plus iy is x. Now let's calculate the other side. Imaginary part of iz. Basically, imaginary part of I times x plus iy. If you multiply I in the bracket, then we have ix or xi, it's up to you which form to write this, plus I times iy. I times I is I to the 2y, so basically it is negative y. What is imaginary part of this complex number? Attention, this complex number is basically negative y plus ix. Always we prefer to think of a complex number in the form of real plus imaginary part times I. So what is imaginary part of this complex number? Imaginary part of this complex number is also x. This shows that from 1 and 2, we conclude that real of z is always the same as imaginary part of iz. I hope by watching this video, now you are a little more familiar with real part of a complex number, imaginary part of a complex number, conjugate of the complex number, relation between them, and how to prove identities about them. If you like this video, please subscribe to my channel and see you in the next videos.